next speaker is Davor Runje. His topic for today is constrained monotonic neural networks. Davor is a seasoned software engineer, computer scientist, and serial entrepreneur. Mostly recently, he co-founded IRT, an artificial intelligence startup building an AI platform as a service for business data. He's a co-founder of Croatian AI League and regularly organizes meetups and conferences. Since 2020, he has been serving as a president of the board of CSEX, Professional Association of Croatian Independent Software Exporters. Among those qualifications, he was an author of many publications in theoretical computer science. Now, we will hear a presentation of an innovative way of building monotonic deep neural networks, outperforming other state-of-the-art alternatives, such as deep lattice network, while using an order of magnitude less parameters. Davor, can you come on stage?
Thank you. I was just wondering, like, how many people are going to scare away with the title? Like, you have monotonic in a title, like, cannot be good. Like, it's going to be boring. Like, cannot be better. I'll start slow. I'll be a bit more technical at the end, because, well, some of you want to see it. But I'll mostly talk about, like, the intuition, how we came upon those ideas. Once you understand, like, the journey, you're going to see, like, most of those things are quite obvious. Like, once you are in the right place, in the right position, looking in the right direction, most of those things are technically not that difficult to do. Like, most people could figure them out. But you have to stand in the right place. If you don't, you're going to be lost. So, I mean, you know, deep learning, highly successful, doing miracles, computer vision, NLP, linguistics, like, it's a miracle. In business applications, not that much, right? Not really. Like nothing exists anymore in computer vision except deep learning. Nothing exists anymore in NLP. I was around 2005 in a summer school in computational linguistics in Stanford, like the state-of-the-art thing. After spending 3 weeks there, I decided, like, not to spend one single minute doing linguistics and computers because that was unusable. Like 15 years ago, well, a little bit more. I'm old. Today, we have things that are like writing articles. Maybe not very good articles, but, like, they're okay-ish. I mean, we can do those kind of things. And the question is really, like, why it's not more popular in business? Business are, like, far more like a standard statistical approach is still, like, in the industry, while the same technique, pretty much, which is completely domain independent, killed everything else. So it's an interesting question, like, why is this happening? And just to understand, like, where the success is coming from. This is one example. It's a word-to-vec algorithm. So what it does, you build very, very simple model trying to predict two words on the left and the right, probabilities. Nothing complicated. You run it, takes some time. Whoever built this algorithm by itself, takes some time, but it's not very complicated. Like, it's a student exercise, if you ask me. And the intuition about this was, like, we have too many words in the language, hundreds of thousands. And we cannot really put this thing mathematically in the model, so we need to, like, reduce dimensionality. So what do we do with these kind of embeddings to go from 200,000 possible words into vectors of size 100, 200, 500, whatever, thousands. But you reduced the dimensionality. So the intuition was, if we have a word that has the same context, appearing in the same kind of things, that's probably the same word with the same meaning. It would be cool to have such a, like, property if you want to reduce dimensionality. The same things go to the same things. Different things, God knows. But what happened, and most of you actually know that this kind of reduction of dimensions actually is preserving a lot of other things. For example, relationship male-female. You have a male noun, you get the same vector, add it to it, you're going to get the female one. That's mind-blowing, like, how this happened. Still don't get it. Okay, male, females, more or less. Grammar. You have present, you want to create the past tense. There's always the same vector. That's easy, that's useful. Political concepts. Like if you know the name of the capital, you can go to the country. From country, you can go to the capital. This is mind-blowing. So why is this mind-blowing? For example, if you look at the translation, 2 languages, English, Italian, what's going to happen with words? They're going to map into the same places. So what that translation does? Take the word, figure out how the sentence is constructed in different language, which is not that complicated. German is slightly different than English. Then you look it up where this word is over there, because it should be somewhere over there. You're done. Simplified, but that's the basic idea. This works like crazy. This was like the key of success of Google Translate. Once you had this trick, everything exploded. So we want to try to do this trick again. Like I want to do something else. Like banking transactions, like the first thing that comes to your mind. You have transactions, people are doing transactions. You have a huge number of point of sales, hundreds of thousands, millions, whatever. You want to reduce dimensions. So what would happen if you try to predict 2 transactions on the left, 2 transactions on the right, basically word to vec, but just with these 10 things. You get a map of Croatia. And of course, things are like, I think I selected something like city budget, city account, because it's like a center of a city where everybody's paying like bills. And then what is like the best restaurant in the city? Well, it's the same vector in Zagreb and Split. So where is the airport? Well, it's the other vector. You see, because it's preserving stuff. So what's going to happen if I take people's history, just replace the old model, whatever the model was, but use this new information about knowing how to encode point to sales. And that thing explodes. Like you get like double the click-through rates. Actually, this is conversion in selling the loans. It's a miracle. Not really unexpected because I didn't do anything like creative. Really didn't. Because that technique exists in linguistics, I just apply it to banking, and it works like crazy, God knows why. We still don't know why it's working in linguistics. That's the other thing. But it works really, really well. The model was the same on the left and the right, and the left one was a good one, the initial one. I know because I wrote it. At least it was the same. Like maybe it's not good, but it's the same thing. But this additional thing that you can actually use this huge amount of data that you have in transactions in this way completely automatically without understanding anything about it. That very simple thing works like crazy. So it's a promising thing, and a lot of people are actually doing exactly the same. Let's use some NLP, like architecture, transformers, whatever. Let's encode those pods. Let's have this sentence now is like your monthly report. Words are like your transactions. Tweak a little bit. Let's see what's going to happen. And it works. But the question is, like, if you really want to be good at something, the question is not what is the same. It's trivial. What is different? What is the difference between business data and languages? So the first thing that comes to your mind is like, oh, it's a different kind of data. This is structured, this is unstructured. But, I mean, it's a sequence of numbers. God knows what it is. So that's not the problem. The difference is in the speed of change. So languages change. Like we change the way we talk every 20 years. Really? Like it's just slow. I mean, my kids will talk different language. I talk different language with my parents. But me, myself, yeah, I'm kind of stuck with it. In business, things are happening on a weekly basis. You have a new competitor. This one goes out of the business. There's a war in Ukraine. Now there's a COVID. There's this and there's that. And you have to constantly adapt. That's one thing. Another thing is like more, I mean, it's the old question, like if you just look like at the history of like Western civilization, what is time? Time is linear. We have past, that's behind us, we go into the future. If you ask people on the East, time is cyclical. Past is always in front of you, and it's behind, because it's going to repeat itself, right? And if you actually look at the data, and this is an example of something, passengers in airplanes or something, I forgot. But I mean, you can imagine. So there's a trend. People fly more and more, right? Or people spend more and more money, or whatever they do. There's a trend. There's like a future, which is clearly different than the past. But there's also cyclicity. It's repeating. Oh, summer again. They will come. right? You know that, like you know both approaches. And the question was really, if this time is special, why are we just like putting everything in like, or ignoring it? It's a different kind of thing. We really have to like, time is not just another feature. It's special. We have to like treat it special. And actually what we did, and this is boring as hell, basically some kind of transformer architecture. But what we did actually, we had like, oh, we're gonna treat time differently. We're gonna like pull it out of everything and put it like in some different highway. There is a highway for everything and there's a highway for time because time is so special for me. I like it. And blah, 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 blah. So what happens? You can break times in different kind of components. There's just different kind of like, you're trying to capture cyclicity in different time periods. But you also say, like, that's not the all. I also want to do it as a line, as just like a flow. So this would be like some kind of integers, classes, whatever you wanted to call it. This will be something that's going to be like continuous, and I want to do both. And that's the easy part. The tricky part is to train it. So actually what we do is we are like quite clever in masking those things. So actually we get the properties of everything. We're trying to like not assume what is going to be the level of cyclicity, but actually just try everything and see what happens. Try all the combination. Try monthly and weekly together with the yearly. Analyze sometimes. So, I mean clients are difficult people. Like, I ask them to give me a data and say, oh, sure, we have data. And they give me, say, look, it's all just data from the past. And they say, oh, sure. And I say, like, okay, I can just, if you give me like data from past, I can build a model to predict the past because I don't have any future in it. And they're like, yeah, sure, but it's kind of useless. We know the past. I mean, we can just look it up. But then I say, like, but what do you really want? I say, like, well, we want to know future. No problem, just give me data from future, I'll build it for you. But again, you see the problem. So you're training on one data set, and you are predicting on the other one, and the intersection is 0. I have no data from 2023. And in December, I'm going to train the model that should work in 2023. And there's not a single data point in it. So what should I do? Well, we are training these things. We are lying sometimes to models saying, you know, like random mutation. It is 21 data point, but I said it's 23. It's going to average out eventually. So if you're really good in doing these kind of things, what's going to happen is, this is some kind of like fraud monitoring, fraud something from IBM data set, and like very cool, fancy transformer architecture. You take special care of time. You go up. And this is the state of the art. And everything else is the same. They also have transformers and all that, yada, yada, yada. But if you understand that time is different, then you can actually do this leap. Because you understand that future is somewhat predictable from past. Somewhat. You can extrapolate certain things are cyclic, but you can actually go and do it. So that was a patent that we filed a year ago, and by the time I retired, then my answer to it. But what happens is, once you start looking into time, the models become more complex. So for example, a typical classification. You have 3 kinds of event that can possibly happen, I don't know, in churn, and 4th one is nothing happened ever. The only probabilities you have to calculate. Once you have a special time, the probabilities changes with time. So this is a static data set. It's actually modeling churn. So what does it happen? So there are like 3 different buttons in your application. This one doesn't happen doesn't happen at all at the beginning. You have to like work your way through to actually get that thing. This one happens a little bit before, and this one you can actually press it immediately. And how to predict when the people will start clicking. And there's also the 4th one. Nobody will click anything. And this is modeled with, I start measuring because I don't have time to wait until infinity. Infinity is nice in theory, but like in practice, difficult to capture. I never had time to wait for it. So you have these 2 well-known things. One is called probability density function. So you're not outputting probabilities anymore. You're saying, I'm outputting the probability as a function with respect to time. So what is the probability of something happening between 3 and 4 hours? Well, This is this cumulative one, integral of that thing. You evaluate it here, you evaluate it here, you take a delta, and there's the probability. My head wants to explode. But it's not that difficult to actually implement it. What is the difficult thing? If you don't have a way to build a function that is monotonic, it will just output garbage, too much noise in data. Because it's calculating the deltas. And deltas will go up and down if this thing is like going up and down like crazy. Because those things are typically very close. So if you allow this thing to go up and down, what is going to happen, the probability will be negative, for example. That cannot be, I mean. So we have, like, if you want to get a good performance on anything that has a special care of time, suddenly we have to know how to build monotonic networks. Problem number one. There's another problem. Not me going to jail, but computer algorithms are today really used to make life and death decisions in people's life. A simple one is like, do you get a loan for a house or not? It's a life-changing experience for sure. In US, you had the algorithm predicting the probability of you repeating a crime, and based on that, you get parole or not. So you either stay in prison or not. Kind of life-changing event, like this algorithm that is outputting. And you would assume these algorithms are like good, right? Or not? You would not, or maybe you would, depends. Like to have this kind of algorithms determining your future. So what happens? Of course, eventually some data points got out. People were looking into who got parole, who didn't, what are probabilities. And guess what? Low scores are good, high scores are bad. Black is bad, white is good. I mean, you can imagine what happened, right? Because for some reason, whatever that reason is, it's actually discriminating by race. It turned out to be a side consequence. It turned out the problem was actually monotonicity, which was handled badly because it had some parameter which was age and didn't handle properly. So what happened is actually they did not really discriminate by color of the skin. They actually discriminated in the wrong way for the age, and of course everything ended up quite badly for some people on the left page, the left side. For the right way, it was okay. Basically, if you want to build something that you could trust to make those kind of decisions, you have to prove certain properties of a model. One of them being monotonicity. For example, if I'm going to give you a loan and you have a higher salary than that person, you should be more likely to get it. That's not always the case. Trust me, if you have seen those algorithms, it's not really the case. Insurance, you're going to estimate what is the possible damage, danger, whatever, all those probabilities. If they're not monotonic with respect to certain variables, they will just give you ridiculous results. Somebody will do the simulation, you will end up here, not in jail, but like in a news article saying males are more likely to get a credit card or whatever. Basically, a lot of those things are just like monotonicity problems. So there's like very strong motivation to have deep neural networks, which are actually monotonic with respect to certain parameters. And it's kind of like an obvious thing. It's like, sure, I need it, let's Google it up, I need to implement this thing, I have like up to lunch. How hard can it be? And after some reading, which took a little bit longer, there are actually two ways to do it, like in general. First, you can do it by construction. So one of the easiest ways, if you have, I don't know, hyperbolic tangent, function is the activation, you can just say, if I keep all my parameters of a neural network positive or non-negative, my function will be always monotonically increasing. Easy thing to do. The problem is, of course, this thing does not never converge in real life, so like, yeah, what can I do with this? Let's move on. The paper's from like 92, 93. It's an old problem. It had a solution while nobody cared, but if you want to use ReLU, LUCell, forget about it. Deep lattice networks. I try to read those papers. I don't have that much time in my life. It's complex. They're huge. I said, okay, I don't really need to understand. Let me just run it on my computer. How do you like download the layer? And I did that. I ran out of the memory and GPU on the real problems. I don't have like money to buy a new GPU. and mine has like 20-something gigabytes, like, that's not the solution. Large number of parameters, like difficult, costs a lot of time. So like, okay, that doesn't work, but it's not that difficult to find some kind of loss function that would just penalize non-monotonicity. And you find a couple of those things. The problem, well, you end up with a function that is not monotonic. What is the solution? I found a new algorithm published a few years ago to actually do the certification. I tried to implement it. God, I don't have that much time in my life. Like, there has to be something simpler. And all of those things cost a lot of resources. So, sure, loss function easy. If I want to do the certification, takes forever. If it fails, I have to go here, here again, until it finishes. I don't have time for that. I'm trying to like build clients per model, and the more I spend on it, like the worse the business is. I want to be cheap, as always, in life in general. So, to understand actually what is happening, and you can actually find this in literature. So if you use ReLU, you can get a monotonic function. There's only one disadvantage, it's going to be convex. You cannot do anything except the convex functions. And actually, the way to see it, if you just use unconstrained ReLU, try to fit something as simple as this, the more neurons you get a better fit. With only 3, you get something that is like, okay-ish. You could live with it, right? It's not really monotonic always because it could go like a little bit down, but like, yeah, it's life, let's just move on. You try to constrain it, what you're gonna get? With 3 neurons, you get this and this. You add more stuff, it's always the same because it has to be convex. And it's kind of a problem because most things that I model do not explode. Like clients try to like model the profits, they never explode, they always go like this. If they go like this, they don't need models. They just like put more stuff in it. They don't care. It's easy to do, right? But if you are like doing concrete work, if it's concave, maybe most likely not, none of those things. But definitely not convex. And everybody's saying like, you cannot do it. Let's just move on. For 30 years. It's ridiculous. So I was like looking into the things and saying like, what if I just don't keep the same activation function, but actually do both convex and concave inside, just to see what's going to happen. I was bored on Saturday. Just try it. 50 lines of code altogether. And believe it or not, this thing works. It works actually quite well. So, again, you put more neurons, this thing is fitting perfectly, but this time, I know this is monotonic because I can prove it easily. It's a trivial thing, like it's really not a big deal. Well, not even a student exercise. So actually, there is a solution. And once I have a solution, let's do it like the properly, like industrial strength language. You put a Python, you write keras, you make a layer, and so on and so forth. So from like 50 lines of code, it like turned out to be huge 100 lines of code. But now it's distributable and everything else. It's like it's really a tiny tweak. Not much to do. And you put it in a larger thing. So this is basically like always the same architecture. So if you see like how the lattice neural networks are applied, basically the same thing. First, they run everything through one monotonic block, then they concatenate or add whatever they do, and then run some number of blocks later, and then do the activation. The good thing is that if you have non-monotonic inputs, you can run it through pretty much anything else. Transformers, convolutions, like whatever you can think of, just run it through it, concatenate, add, whatever, do it is. What you get is actually quite strong properties. First, you can control monotonicity, both increasing and decreasing. You could also control convexity and concavity of functions, which means you have perfect control over the first order derivative and second order, I mean being greater or less than 0, which is basically what you need in most applications. Most applications, you know, things are going up, but they go into saturation. Like 90% of my use cases are like concave with a saturation. Like you have increasingly, sorry? Okay, anyway, let's just move on. How does it work? Compared to pretty much everything, this is like the real industrial standard, deep lattice networks. So you get a boost in the accuracy, pretty much across the board. But look at this thing. 31,000 compared to 100. 2.5 orders of magnitude. This is a toy example, and this is this compass for doing the pearls. Once you put this thing in a big, large networks, this thing like goes big. I mean, with lattice, I typically run out of memory very soon. On like 20 gigabytes of GPUs. I need to control that thing. It's not so easy. But here, this is nothing. It's just another layer, a dense one, like the simplest possible thing, like 100 lines of code, like if you want to get like production quality of the thing. And basically last week we finally did all the like previous work, research and so on, and filed it as a patent into US patent office. Filing a patent is quite exhausting exercise. So it's not just you have idea. Like I implemented the first thing over the weekend. 50 lines of code. Like industrial strength, in a few days, 100 lines of code while I finish everything. But this thing takes 2 months because you have to go through like 30 years of research and find anything, how you're different than anyone else. And it's just amazing that there's such a simple trick of just combining concave and convex activation function can produce a model that is like superior to everything else. And that will be all for me. I mean, questions, thoughts, slow clap. No, slow clap first.
Great presentation, thank you very much. Actually, the question is, in patent you usually don't write what domains are limited domains, but my question is, on which domains did you test this approach? And maybe signal-wise, what kind of signals did you test? And it worked? Thank you.
Yes, thanks. Thank you for the question. Like, I like to do this. I hate real-world data. I never do that. So I do have Sharat who is working with me, and he's quite actually good PhD student, and he does this like boring data, real data stuff. What I love to do is actually, I generate synthetic data sets. Because if you have a good synthetic data set, which you control perfectly, you can test any single hypothesis that you have, and you can do it like this. Because what if this variable is from gamma distribution and this is normal, and what if this is uniform? I cannot find a data set like that, but I can write it in an afternoon. So when I do research kind of things, I don't really look into real-world data until I'm perfectly comfortable that I know what I'm doing. Because there's so much noise coming in that I never know, is it because of the input pipeline or the data or somebody just dumped the data in the wrong way or whatever happens. But if I have a synthetic data set which I generated, and I know how I did it, and I did all the testing and statistical testing and everything on it, and I'm quite confident that this is good, then I'll have much, much better results, and I'm much quicker to iterate. Because something is not working, is it the data or is it the model? Is it this or that? I don't have time for that. So basically, I always work on synthetic data sets. Like the thing, and there's a reason why in each of my paper, the results on the real data sets are like the last thing on the last page. I typically don't even read it. I like look at the results, oh, they're bigger, better, cool, let's move on. Like because if you want to, I actually learned that some long time ago. I had the research career, and it was more like computer science. If you really want to understand the concept, you need to start with small examples. Because big ones are too complex. There are like way too many things going on, and you never get the real answer. You never know what is real. So you really have to reduce. So, I did most of my testing on fitting the cubic curve. Like, can you imagine the simpler curve that is neither convex, concave, and it's not linear? I could not think of anything simpler than that. And that thing was enough. And there was like no special thing, not plus something. No, x to the third. And once you do that, once you gain these kind of things, then you run through all these kind of like a standard data sets and all that stuff. But you don't learn on them. You just like confirm your knowledge, in my opinion. But thank you for like having me a good reason to tell you why I hate this.
Do we have more questions? Okay, I guess everything is clear, and thank you for your amazing talk.
Yeah, thank you.